Hey fourth grade, Ryan here. Hope you guys are doing super awesome and you had a great time during our lesson last week. This week we're going to talk a little bit more about the earth and we're going to talk about earthquakes and how they relate to engineering. So I hope you guys are excited to do some more science. So you may remember from what Mr. Andre and Miss Ariel said, right, that the earth is made up of these things called tectonic plates, right? They're under the crust, you can't see them, and they kind of fit like a jigsaw puzzle, right? So we have all these pieces of the earth that are slowly moving around below us and we don't even feel it. Now, because they're moving, there's the possibility that maybe they slip past each other or they hit each other. And then what happens? Does anyone know? So if you thought that the answer was earthquake, then you were spot on. And the earth is actually having many earthquakes millions of times per year, right? We just can't feel them because they're not strong enough. But every once in a while, the plates hit in such a way that it's actually, you can feel it for miles, thousands of miles even away from where the plates actually hit or slip past each other. If you were living in California last summer, on the 4th of July, actually, we had the Ridgecrest earthquake, and it was one of the largest earthquakes in recent memory, right? You feel the ground kind of shaking, right? And you have no idea what's happening. It's these tectonic plates are moving past each other. So you can see an example of these tectonic plates meeting each other in the diagram I have for you here. So we have tectonic plates meeting at a fault line, and what happens is when they collide at this fault line or they slip past each other, we actually get the motion that causes the vibrations of an earthquake. So you may notice that I've been walking around, right? So I'm at Caltech's campus right now, and so this building behind me, then it's called the MUD building, basically. So there's a north and a south MUD, and what these buildings are is sort of the cradle of earthquake research, right? Some of the smartest scientists in the world work in this building right here, right, to figure out, how do we measure earthquakes? When do we know? Can we tell when they're going to happen? And they want to figure out all the science and engineering that happens because of earthquakes. You might be thinking though, why do we even care, about these earthquakes, right? They only happen maybe once a year and, feel a little shaking, right? And it's not that bad. But the problem is that earthquakes can actually be really deadly, right? We measure the magnitude, right? Which is basically the scale of how bad the earthquake is, right? So what I've done is I've attached a YouTube video that I want you all to watch that shows just how devastating these earthquakes can be to our buildings and to our infrastructure. So check that out right now. So you might have heard me say that we can measure how powerful the earthquake is on a scale, right? And we call this the Richter scale. So basically what the scale tells us is just how powerful an earthquake is. And this scale, typical range is maybe from 1 to 8. So if we have a magnitude 1 earthquake, right, we think, it's not so bad, it could be worse, right? If we had a magnitude 8 earthquake in California, some people call that the big one, right? And would have pretty bad damage, right? The bridges would be shaking, the buildings maybe even falling over, who knows, right? So these things can actually be really devastating. So as engineers, we need to know how we can design our buildings to prevent against damage from earthquakes. So previously I was an engineer in Florida, right? So I'm gonna put my engineer's hat on, right? So my John Deere hat. So this is my engineer's hat, right? And I wanna try and figure out how can we design a building that can withstand an earthquake. All of us are going to figure that out together and do a little experiment. So you'll need a couple of ingredients to do this. So this can be anything you can find in your kitchen. It can be graham crackers and frosting like Miss Ariel showed you last week. It could be noodles, it could be toothpicks, it can be popsicle sticks, marshmallows, whatever you find. Let's go in my kitchen right now and see what I have. All right, so none of this looks good, but got the pantry. All right, I'm not really liking any of this. What have we got? Hot marshmallows. That'll work. So you got some pastas up there. Oh, noodles. Great. That's all we'll need. All right, so I came back outside. Got my marshmallows here. Got my thin spaghetti here. So what I'm gonna do is I'm gonna design 2 buildings, right? And then we're gonna pretend to have an earthquake and we're gonna see how well my buildings hold up. All right, so with my spaghetti, I'm just gonna start and I'm gonna start breaking it in half. And you don't have to do this even if you don't have spaghetti, right? You could be using toothpicks, you could be using popsicle sticks or anything. I just want my pieces to be a little bit smaller than they are, so I'm gonna do that. Alright guys, so I finished building my structure and yours could look completely different than mine, and that's perfectly fine, right? So what I built is called a truss. Now in civil engineering, trusses are one of the most common types of structures, right? Because they're very simple. It is almost like a jigsaw puzzle, you know, kind of just like how the tectonic plates are beneath the Earth's surface. So what you can see is the marshmallows represent what we call pins, right here and here. And the noodles are called beams, right? So the beams and the pins together make up this truss, okay? And all of the noodles are perfectly the same length, right? And I've angled it in just a way so you can kind of see all the different pieces, right? So I have 6 noodles up here, 6 marshmallows, excuse me, 6 marshmallows up here, 6 marshmallows down here. So we want to see, is a truss the best type of structure that we can use for an earthquake? So what I'm going to do is I'm going to start shaking the table. We're going to see what happens. All right, so I'm shaking the table a little bit, and you can see that what we have here kind of happening is that there's not any square anymore, right? You can see how this guy is almost falling over, right? So that's not very good. We don't want our buildings falling over like this. And you can see the more I shake, the more it kind of becomes bent. Now it's triangles, and these literally used to be squares. So this is not a great design. So what happened, right? So I said this truss is like the best structure in all of civil engineering. And this is actually true, right? If you go into maybe the gymnasium at the school or somewhere else, right? If you look up at the ceiling, it looks exactly like a truss, right? It's all these interconnected beams together, right? And so that is a really good structural design. But the problem here was the shape of my truss. So what I'm gonna do now is I'm gonna redesign my truss, and I'm gonna show it to you guys. Alright guys, so I'm not that smart. My design didn't work on the first time, but maybe yours worked on the first time, and you have designed a building that beats an earthquake, and that is awesome, right? So as an engineer though, I know a lot of people who are really smart, right? And so I think back to that, right? And I changed my structure a little bit, and I don't know if you can see what's different about it, right? But I've added triangles to it, because triangles are the most important tool that we have as civil engineers. I'm going to show you why. So I've drawn both of my trusses right here. Here's the first truss I drew, and here's the second truss I drew. So if you imagine the wind is blowing down on your building, right? Or maybe you have an earthquake that's shaking it. It doesn't matter. You can see immediately here, right, that my truss here, the new one that I built, has many more beams where I can distribute the force that's being applied to it. So the wind has many more directions, many more beams that are taking up the force. That's why the triangle is the most important type of truss design. All right, now that we know a little bit about the science behind the trusses, let's see if it actually works. So what I'm gonna do again is make my earthquake and see how fast my building falls. All right, so again, I'm shaking the building, and it's really good to view it right here, right? And you can see practically nothing is happening, right? So I'm shaking, and maybe this first little guy is falling a little bit, but overall the structure is actually really maintaining its shape, right? We've been going for almost 10 seconds, 15 seconds, and nothing is happening. All right, so I hope you all had fun today making your buildings and trying to prevent an earthquake from taking that down. So if we just recap on what we learned today, we said that the scientists tell us that there's tectonic plates, and sometimes these plates hit each other or they slip past each other, and that creates what we call an earthquake. So these large vibrations present a big danger to some of the buildings that we live in. So as engineers, we put our engineering hat on, and we said, how can we make a building that best supports itself against these earthquakes? So in my design, I used a truss, and I saw that the triangle truss actually did a really good job of holding up my noodles and my spaghetti. And then we see that in real life, the triangular truss is actually one of the best civil engineering structures we have. It's simple, it's easy to build, right? So it's awesome for engineering. So I hope you guys learned a lot today, and see you next time.